And what we are going to do is find f prime of x using the definition. Okay, so what that means is that is a problem just like we have been doing. The definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. And once again, if the directions on the quiz or the test say use the definition, then make sure you actually use the limit definition of the derivative. And you will get more points for sure for an incorrect answer where you tried to use the definition but made mistakes than if you just ignore that part and just write down an answer using the shortcut. You won't get any credit for that if it says use the definition, because that definition is what I'm really testing for in that problem. Okay, and I know you haven't been too tempted to do that until today, but you'll see what I mean if you don't already. All right, but I am going to use the definition here. So just like we did for the homework, all right, I need to find f of x plus h. But notice f of x equals 7. So if f of x equals 7, can you tell me what is f of x plus h? What do I get when I evaluate that function at x plus h? Yeah, we would get 7 times x plus h. I'm going to erase it. Don't write this on your paper. If I had an x here and I plugged in x plus h, then I would get 7 times x plus h. I'm going to ask you kind of an easier one first. So forget about this derivative for just a second. So back to algebra class, because I know this one looks funny. If I ask you to find f of 1, if f of x equals 7, what do I get for an answer for that one? If I'm just evaluating f of 1. So forget about all the fancy stuff. So I mean, it's like I'm in college algebra class and I'm just going to graph that function. What is f of 1? Yeah, it's 7. Good. What's f of 8? So if we plug 8 into that function, what would we get for an answer? Yeah, we would get 7, right? And if I find f of negative 349, I get 7. This is a constant function. This means no matter what I plug in for x, the y value is always going to be 7. So if I find f of x plus h, that's just 7, because it doesn't matter what I plug in for x. F of that is equal to 7. That's what it means to be a constant function. But I know it looks kind of funny, so people hesitate to write it down at first. Okay, then I have minus f of x, but we can see that f of x equals 7. So if I simplify that, I have the limit as h approaches 0, okay, of 0 over h. Now notice that when we take the limit as h approaches 0, it doesn't matter what happens at 0. That h is not actually equal to 0. That just means what happens when we get close to 0. And as we get close to 0, 0 over h, because this number, notice this is not equal to 0, right? It's either to the left of 0 or to the right of 0. And if we put 0 over any number that's not equal to 0, that actually simplifies to 0. We have 0 over something other than 0. 0 over 0 is undefined, of course. That's why I made a big deal about that. We have to know that h is not actually equal to 0. But then, if I take the limit of a constant, I always get that constant. So the limit as h approaches 0 of 0 is just 0, which means that the derivative of that function that I started with Okay, so the derivative of our function is equal to 0. Which makes sense, right? If we think about it, if we graph f of x equals 7, that's a horizontal line at 7. And remember, the derivative gives you the slope at any particular point, and we know the slope everywhere is equal to 0. So any question about what we're saying there? Now what I want you to notice is there's nothing special about it being f of x equals 7, right? If I started, let's say, with g of x is equal to pi, and we use the definition, we would say the limit as h approaches 0 of g of x plus h minus g of x over h. But notice, when we find g of x plus h, it's just a constant again. G of anything is equal to pi. So do you see the same thing happens? We're still going to get a 0 over h, just like we did up above. So just to save us time, I'm going to write 0, but we're going to get the same steps that we had up above. And that will always happen if that function is just a constant. So we're going to extend that to be a rule or a formula, right, that says that if we take the derivative of a constant, so this c that you see here, the derivative of any constant with respect to x is 0. So using this notation up above, we took the derivative of 7 and we got 0. And then I took the derivative of pi and got 0. So we could go back and use the definition every time, but we don't want to take time to do that because it's always going to look the same. So again, if the directions don't say we have to use the definition of the derivative, from now on, if we want to take the derivative of a constant, we're going to know that the derivative of that constant is equal to 0. So any questions about that rule before we go on? So the derivative of every constant is 0. That's going to save us a lot of time. Okay, so let me hear from everyone else because I want to know if that's okay before I keep going. Okay, I could go back to the definition of the derivative for every one of these, and I'm not going to do it for all of them. I can show you particular examples for the power rule where I have like an x to the first and an x squared. After that, we have to use the binomial theorem and it gets really messy to go back and use the definition of the derivative, but that's where it comes from. But the power rule says that if I take the derivative of x to some power, notice that n was the exponent. So do you see, like if I had an x to the third, that would be a 3. In fact, let's write that down as an example underneath here. So if I take the derivative of x to some power with respect to x, notice these variables match. That's important. Okay. So the power rule says that I can drop that power down front. So this is a 3x, and decrease the exponent by 1. So if I decrease that exponent by 1, I would get 2. So if we use the definition of the derivative and worked it all out, that's what our answer would turn out to be. So from now on, if we just have x to some power, then we are going to use the power rule to take the derivative. Unless the directions specifically say to use the definition, then we will do that. Okay, so I'm going to practice a couple more using the power rule before we go on, just to make sure that you see that you can use the power rule on anything that can be rewritten as x to some power. Okay. So for instance, if I have f of x is equal to the cube root of x squared, and I want to take the derivative, Well, notice that right now, it does not look like our power rule. So if you have a radical, what you will want to do is rewrite it so it looks like x to some power. Can you guys help me out? If I have the cube root of x squared, that is x to what power? Yeah, exactly. That's x to the 2/3 power. So when we have radicals, we're going to change them to exponents to make it easier to take the derivative. Notice that's equal to the original function, so be careful. Make sure you don't write x to the 2/3 here. I'm going to erase that real quick, okay, because it shouldn't be there. That's not the derivative. That's equal to the original function. But now we're going to use the power rule to take the derivative. So the power rule says we can drop the exponent down front, so that's 2/3 x, and then we decrease the exponent by 1. So what is 2/3 minus 1? What's 2/3 minus 1? Yeah, 2/3 minus 3/3, so that would give us negative 1/3. And that's our derivative. Any questions about what I did there? Hopefully it doesn't matter to you at all which way we write our answer. So if it doesn't say write it a particular way, my strategy usually is to mess with it as little as possible so I don't make a careless mistake. But as a general rule, we want to write our answers in the same form it was given, and we definitely need to be able to do that. Like on this problem, when we are in the next chapter, we are going to have to rewrite that to be able to finish our problem. So let's just practice doing that. So it's a negative exponent, so I know it's in the bottom. So I'm going to just put an extra step in there first. Okay. And then instead of writing x to the 1/3, I could change that back to a radical. That's just the cube root of x. And again, just follow the directions. So the directions may say, don't leave negative exponents in your answer. Or it may say, don't leave fraction exponents in your answer. So if it says something like that, it means that it wants you to simplify it. Sometimes it just doesn't matter if it doesn't specify. Again, I don't mind if you leave it like that for now, but you definitely will have to be able to change it. So if you're not sure that what we're doing when we rewrite it, please ask so we can get it straightened out. All right, let's try another one. Okay, so if I want to find the derivative of f of x equals, let's say I have 1 over x to the 7th. You cannot say that that's the derivative of the top over the derivative of the bottom, right? That doesn't work. We're going to talk about that some more in section 3.4. So what we're going to have to do is rewrite that so that it looks like x to some power. How can I rewrite 1 over x to the 7th so it looks like x to a power? Yeah, that's x to the minus 7. Good. And once you have rewritten it like x to some power, so now I'm taking the derivative of x to the minus 7th. Notice the derivative is an operator there. So we have to take the derivative of something. So the power rule says that I drop that minus 7 down front. I decrease the exponent by 1. Minus 7 minus 1 is minus 8. And then I'm going to rewrite that as minus 7 over x to the 8th. So any questions about that one? Okay, so anything you can rewrite as x to some power, you can use the power rule. Okay, that was one from earlier. Sorry about that. Okay. Okay, so more rules. Okay. The next one is the constant multiple rule. And you can see it written out there. It says that the derivative of a constant times a function is that constant times the derivative of the function. So what that means is if I have something like I'm taking the derivative of 4x to the third. What this rule says is that since this 4 is just a constant, you could pull it out front. That's what it really says, that you can pull a constant in front of the derivative. And then we already know how to take the derivative of x to the third. That's one we did earlier. We dropped the 3 down front, decrease the exponent by 1. And notice then we would get 12x squared for the derivative. So whenever I say that the derivative of a constant times a function is a constant times the derivative, that's what I mean. You can pull a constant through the derivative. Make sure you never pull anything in front that has a variable in it. And as we practice, you're going to notice we won't put in all those steps every time. I just wanted you to see, okay, what we're really doing. But then notice that if I just take 3 times 4, that would give me the 12. And that's the way we'll usually think about it. We won't usually put in these middle steps. I just wanted you to see that we're using that rule. When we say 3 times 4 is 12 and then decrease the exponent by 1. The derivative of a sum of two functions is the sum of the derivatives. So that means that we can find the derivative of each term separately. So to just give you a really small example before we do the next ones that you see on the sheet, it means that if you have something like this, let's say that I have x to the fourth plus x squared plus 8. And I want to find the derivative of that function. Let's make one of those a minus because it doesn't matter if it's a plus or a minus, it works the same. We take the derivative of the first term, which is 4x to the third. And this rule says that you can just take the derivative of each term separately. So now we take the derivative of x squared. What will I get when I take the derivative of x squared? Yeah, 2x. Good. And the derivative of minus 8? So everyone tell me, what do I get when I take the derivative of minus 8? What about everyone else? If you haven't given me an answer yet, do that real quick. And it's okay if you make a mistake. If you do, we'll straighten it out. Yeah, the derivative of any constant is 0. Very good. I'm only writing the 0 for emphasis. We wouldn't normally write it down. Okay, but that is what the sum and difference rule tells you. If they're added and subtracted, you can find the derivative of each one separately. And again, all of those go back to that definition of the derivative. E to the x is our best friend in calculus class. Sometimes my college algebra students try to avoid it, but it's the nicest function we have. The derivative of e to the x is actually itself. So anytime we want to take the derivative of e to the x, we will get e to the x for an answer. Okay, so let's see if we can use those derivative rules. So for the first example that you see here, okay, I want to find the derivative of that function. And the first thing I would do is notice that we have some terms where it doesn't look like the rules we have done so far. So we haven't talked about one with the fraction yet, unless we can rewrite it as x to some power. The radical we need to rewrite. So before we take the derivative, let's rewrite that function. So instead of 5 over x squared, I can write that as 5 to the x to the minus 2 plus cube root of x to the 5th. How can I rewrite that as a power of x? Yeah, that's x to the 5/3. And again, notice that I did not take the derivative there. All I did was rewrite that function algebraically. And definitely don't take the derivative of some terms and not others, right? So this is the original function. Now, when you take the derivative, don't just write equals here. So I'm going to go ahead and do this first term so you can see what I'm doing. If I take the derivative of that, 3 times 6 is 18. Decrease the exponent by 1. Okay, and we can finish taking the derivative. Some of you may be doing that on your paper. That's great. But if you leave it like that, you're going to lose points because you're telling me that that's equal to the step before, but it's not. The step before, the one I have in pink, is the original function. This is the derivative. So make sure that you label them correctly. So what you say is the original function, make sure it really is. And what we say is the derivative, make sure it really is. But then we're going to keep going. So you guys tell me the next one. When we take the derivative of the next term, what do we get? We have 5x to the minus 2. What's the derivative of that? Okay, so I'm seeing a minus 10. That looks great. So minus 10x, but the exponent on my x should not be 1. Good, it should be negative 3. You have to subtract 1. And I know that it's easy to make an arithmetic mistake there, so just be careful. The next one, same thing. Drop the 5/3 down and then subtract 1. 5/3 minus 3/3 is 2/3. And the derivative of the last term, when I take the derivative of pi squared, what would I get? What's the derivative of pi squared? Now the derivative of x squared would be 2x. That's true. Okay, but notice that pi squared is a constant. And the derivative of every constant is 0. So the derivative of pi squared is 0. So this is the derivative of my function. If you take the derivative of x to some power, that's when you use the power rule. And I know that that looks a little funny. Okay, so I just wanted to make sure that didn't trip you up later. That's why I asked you that, but that's just a constant. So any questions about that? Now the next one, after we do section 3.4, you would have a choice which way to work number 2, but even then, the way we're going to work it in this section will be easier, so most of us would choose that. Notice that I have a product. We are going to have a product rule, but for right now, I'm going to rewrite that so that I can use the power rule. So when you see this square root of x, remember that means x to the 1/2. So I'm going to distribute x to the 1/2 through those parentheses. So every term just looks like x to some power. And when we multiply and the bases are the same, what do we do to the exponents? So when I multiply x to the 1/2 times x squared, what will happen to my exponents? Yeah, we add them. So we have 1/2 plus 4/2, so that's x to the 5/2. X to the 1/2 times 4. And notice how I have that written as equal to my original function, because we haven't taken a derivative. We just rewrote that function. Now we're going to take the derivative using the product rule. So x to the 5/2, we bring the 5/2 down. We subtract 1. So 5/2 minus 2/2 would be 3/2. 4 times 1/2, so that would give us 2. X, and what will the exponent be on that x when we take the derivative? Good, negative 1/2. 1/2 minus 1 is minus 1/2. So the point of those problems is rewrite them so that they look like the rules we have done. Okay, so far that's been the constant rule, the power rule. If we're lucky enough to just have an e to the x, it's its own derivative. If they're added or subtracted, those are the ones that we have no problem with. Okay, you're still going to have those tangent line problems. So it says write an equation of the tangent line to the curve at a equals 0. The only difference now is you don't have to always go back and use the definition of the derivative unless the directions tell you to do that. So instead, okay, I still need to find the derivative because I know that's how I'm going to get the slope of the tangent line. E to the x over 4 is the same as 1/4 times e to the x, so I'm just rewriting it like that to just make it look a little easier. But try to get used to seeing that written either way so you don't do extra work by using more complicated rules when you don't need to. All right, so when we take the derivative, we know that if we have a constant times the function, that the derivative is that constant times the derivative of that function. And the derivative of e to the x is e to the x. What's the derivative of x to the first? So notice this is x to the first. So what do I get when I take the derivative of that? Good, 1x to the 0. Good. And x to the 0 is equal to what? 1. Good. So the derivative of x to the first is just 1. So remember, this is what we did, okay? But x to the 0 is just equal to 1. All right, so this is our derivative. But now we need to find the equation of the tangent line when a equals 0. So remember, you have to find the slope at that particular point, which means we need to plug 0 into our derivative. So if I plug in 0, I would have 1/4 e to the 0 minus 1. But e to the 0 is just 1. So 1/4 minus 1 is negative 3/4. And I need a point, and we are given that we are trying to find the equation of the tangent line at a equals 0. So our x coordinate is 0. To get the y coordinate, always go back to your original function. If we plug 0 into that original function, what will I get? Good. We get 1/4 times e to the 0. Good. 1/4. And then once you have a point and a slope, you guys know how to write the equation of the tangent line now. So y minus the y coordinate is equal to the slope times x minus the x coordinate. And if you noticed you were given the y-intercept, of course, you could just go ahead and put it in slope-intercept form from the get-go. Okay, but that's the equation of the tangent line to that point. So any questions about that before we go on? The other thing that you're going to see in this section is how to take what we call higher order derivatives. And so far, we have been taking first derivatives. And so we've already seen this in class before. These are the different notations you can see for the first derivative. So I had these on a slide back in section 3.1. And we have been using this one and this one a lot. We've used this one a little bit. I'll try to make a point to write some like that so you're used to it. That one you use more when you get to calculus 3, although you will run into it occasionally before then. But it means the same thing, the derivative of y with respect to x. Okay, so as long as you're taking the first derivative, those look exactly like the ones we have done so far. But we can also take a second derivative. And when we get to chapter 4, you're going to start seeing more information about what those higher order derivatives tells us about a function. So for right now, it's just going to be evaluating them. So we'll talk more about what that means as we go on in our course. But notice the notation for the second derivative. Do you see you have 2 primes there? And the 2 primes mean second derivative? This means the second derivative of y with respect to x. So don't read that as d squared y over dx squared. We're not squaring anything there. That really is a notation that means the second derivative of y with respect to x. Same thing here. That is not an exponent. That is telling you to take the second derivative. And to take the second derivative, if I didn't tell any of you what to do to take a second derivative, I bet you would do the right thing. So I'm going to do an example before I move on and talk about the rest of this slide. Okay, so if I have, let's say, the function d dx, or let me write it as the original function first, and then we'll find the derivative. So if my original function, let's just say, is x to the third plus 7x squared minus x plus 5. All right, so there is my function. And I take the first derivative of that function. That's what we have been doing. So I know you guys could tell me that. So that's 3x squared plus 14x. Remember, the derivative of x to the first is just 1. The derivative of a constant is 0. So it looks like that. So whichever notation we use, okay, that's the first derivative. And to take the second derivative, you just take the derivative of that function, right? So that means now if I take the derivative of this function in the previous step, so do you see what I put there? So I'm taking the derivative of the function in the step before. So I bring the 2 down, I get 6x. The derivative of 14x, what would that be? Yeah, that's just 14. Good. The derivative of 1 is 0. So that's the second derivative of that function. So the second derivative is just the derivative of the first derivative. You can take a third derivative. You can keep going, right? So if we take a third derivative, notice the notation looks similar. There's 3 primes. And again, We're not raising anything to the third power there. That notation means that you're taking the third derivative of y with respect to x. So that's how you should read it to yourself. And I can do that up here. So in this problem, if I find the third derivative, notice I take the derivative of the second derivative, and I would just get 6. Then the primes become too cumbersome. So in general, if we have a derivative that is of higher order than 3, we don't write primes anymore. We use this notation. So notice it looks like an exponent, but do you see it's in parentheses? If it's in parentheses, that tells you it's not an exponent. That means the derivative. So in this example that I have up above, if I am finding the fourth derivative, do you see I'll put the little 4 there? You know that doesn't mean y to the fourth because it has parentheses around it. And if I find the fourth derivative there, I'm just taking the derivative of a constant, so I would get 0. Okay, and again, we'll talk about what those higher order derivatives tells us about the graph when we get to chapter 4. But any questions about how I got it there? Any of those derivatives? Takes a little while to get used to the notation, okay? All right, so notice in this example, the question says, find the third derivative. So if you are supposed to find the third derivative, you're going to start by finding the first derivative, and then you're going to find the second derivative, and then the third derivative. And these problems that I have right here, I want you to do those on your own first, and then we'll do them together. So to give you time to do that, and I still want you to be able to take a break and stretch out a little bit. So let's take a break a little bit longer than normal. So let's say about 15 minutes, okay? And then we'll come back. So and actually write those down, and then we'll do them together to make sure that you've got it. So it looks like that'll be about 10 after. So let's come back at 11:10. And in that time, both take a break and find the third derivative for each one of these problems. And we'll talk about them when you come back. But any questions before you go to do that? $11.10, Daniel. So 10 after. You're welcome. Hi, everyone. Please let me know if you can hear me. I hope that you're back. And I have worked those 3 problems so that you can check yourself or tell me if I've made a mistake. So let me hear from you. Did you get the same things that I got when you found the third derivatives of those functions? If you have a question about any of them, please just unmute yourself and ask. That's great, Grace. What about everyone else? Did you get the same answers that I did? Thank you. All right, that sounds like those are going pretty well then. Okay, so the next problem does look a little different. It says find all points on the graph where the tangent line is horizontal. Okay, help me out. If the tangent line is horizontal, what do we know about the slope of the tangent line? The tangent line is horizontal. What does that tell us about the slope of the tangent line? Yeah, the slope is equal to 0. Very good. And if the slope of the tangent line is equal to 0, that means that the derivative of our function is equal to 0, right? Because the derivative gives us the slope of the tangent line. So if we want to find the points where we have a horizontal tangent line, we need to find the derivative of that function and set it equal to 0. So let's just do that for this problem. So notice we can use our power rule. If I take the derivative of x to the third, I would get 3x squared minus the derivative of 27x. So that would just be minus 27. The derivative of 5 is 0. So notice that I took the derivative and set it equal to 0. That's how we will figure out where we have a horizontal tangent line. And you can factor that if you want, or since it doesn't have a middle term, if you want to just isolate x, that's okay. So I'm going to add 27 and divide by 3. We get x squared equals 9, which means x is equal to what? Yeah, one of the answers is 3. What's the other answer? -3. Good. So we're going to have 2 points, and notice that the directions say find the points on the graph. So points are ordered pairs. They have an x coordinate and a y coordinate. So for each one of those, we need to find the y coordinate that goes with it. So we're just going to plug it in, right? So let's plug in 3. So 3 to the third is 27 minus 27 times 3 plus 5. So I'm just punching at my calculator. So you guys do that too and make sure we get the same answer. But it looks like I'm going to get minus 49 for that one. And I got 59 when I plugged in minus 3, but please tell me if I made a careless mistake because I'm trying to talk and put it in my calculator at the same time. Sometimes I'm a little challenged. But any questions about what I did there? So if it just says, where do you have a horizontal tangent line? You could just give the x coordinate. But if it asks for a point on the graph, make sure you give both an x coordinate and a y coordinate. Okay, so now we are going to move on to section 3.4. And section 3.4 is about the product rule and the quotient rule. So what you see here is a statement of the product rule. The product rule says that if you take the derivative of the product of 2 functions, so your functions are multiplied together, so you're going to see some examples of that in just a little bit, that will always be equal to, notice that that is, I will say it as the first function times the derivative of the second function plus the second one times the derivative of the first. So here I have it written out in words the way that you will hear me say it. Okay, so that's very informally, but this is the statement of the product rule. The first times the derivative of the second plus the second times the derivative of the first. And before we go on, I want to show you that that comes from the definition of the derivative. Everything that we do is going to go back to that definition. So I am going to find the derivative of this product using the definition of the derivative. And so we know that the definition of the derivative says that you're going to find the limit as h approaches 0. And you need to plug in x plus h into your function. So notice if I plug in x plus h here, I would have f of x plus h times g of x plus h minus the function that you're taking the derivative of. Okay, so that is the definition of the derivative of that product. And we can try to substitute in 0 right now, but you can see if I do that, I'm going to get 0 over 0. So I know I have more work to do. So I am going to rewrite this function. So notice I'm making a big long fraction bar here because what I'm going to do is, let me write what I have up there right now in blue. But so I hope that it's more obvious to you that I don't change the problem. Do you see how I'm leaving that big space in the middle? So if you're writing that down on your paper, leave that big space in the middle. All right, that's what I have using the definition. But now what I'm going to do is add or subtract the same thing in the middle. So I'm not changing the problem. And you'll see why I want to do that in just a minute. But I want to subtract f of x times g of x plus h. But I can't change the problem. So if I subtract that, then I need to also add it. So do you see I'm really just adding 0? So it's just like writing minus 3 plus 3 up there. I really haven't changed it. I just made it look different. And I know that looks a little funny, so I'm going to show you why I wanted to do that. Because now what I'm going to do is split this fraction apart. So I'm going to have the limit as h approaches 0. And I'm going to group it like this. So I'm going to put these first two together. And just to save a step of writing, notice that if I put these first two together, do you see that they both have a g of x plus h? So I am going to factor that g of x plus h out of those first two terms. So if I take g of x plus h out of this first one, I would have an f of x plus h left. If I take the g of x plus h out of the second one, I would have f of x. Notice if I distributed that g of x plus h, I would get this back. And I know that the limit of a sum is the sum of the limits, which means, do you see I'm writing the limit in front of these separately? That was one of our limit laws from section 2.3. And I'm going to group these last two together. And notice they both have an f of x, so I'm going to factor that out. So if I take f of x out of the first term, I have g of x plus h. If I factor the f of x out of this, I would have g of x. And if I put all of that back together, I would have the same thing I have in the step up above. Definitely made it look different, but I did not change the problem. Okay, but I'm going to pause there for a second to give you a chance to ask if you have a question about that. So any questions about what I did there? because I'm going to rewrite it again. Because we had another limit law back in section 2.3 that said the limit of a product is a product of the limits. That's not true for derivatives, but it is for limits, which means that I'm just looking at this first one that I have right here. Notice that's g of x plus h times that second one. So we have a limit law that says I can write that limit in front of each one. Notice if I multiply these two together, I would get what I have in the step above. The limit of a product is equal to the product of the limits. Same thing for this second one. I can rewrite that as the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x over h. And I hope that's starting to look a little familiar to you. Because I know you know what this is. Do you see that where I have the limit as h approaches 0 of f of x plus h minus f of x over h? What is that equal to? Just this part. What is that? I hope you recognize that. Yeah, that's the definition of the derivative of f with respect to x. Right? That is exactly what we mean when we write f prime of x. That's the derivative of f with respect to x. Notice here, if I take the limit as h approaches 0, if I plug in 0 for h, that's just g of x. Right? I just substituted in 0 for h. So notice I'm not writing the limit anymore because now I've evaluated the limit. Same thing over here. Notice the limit as h approaches 0 of g of x plus h minus g of x over h. That is just the definition of the derivative of g with respect to x. Which leaves us with this guy. The limit as h approaches 0 of f of x. Notice there's no h here. So as far as this limit is concerned, we're just taking the limit of a constant, right? Because our variable for that limit is h. So the limit as h approaches 0 of f of x is just f of x. So notice we started by taking the derivative of this product, and this is what we get for an answer. And that's exactly what the product rule says. I think I have them written in a different order, but we know that if we're adding, it doesn't matter which one we write first. I have this one written first below. But the point of that is the product rule comes from the definition of the derivative. But we don't want to go back and put in those steps every time. So instead, we're going to remember that the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. But any questions about that before we work a problem where we use the product rule? All right, so now let's practice using it. Okay, so notice in example number 1, I have a product. I have one function times another function. So if you're comparing it to what we have up above, this would be the f of x. This would be the g of x. Notice I'm taking the derivative of a product. So when we take the derivative of the product, we write down the first one, which is e to the x. Notice I didn't do anything to it. I just copied it down, times the derivative of the second one. What's the derivative of x minus 2? and I'm going to stall just a minute to give you time to tell me, so I'm going to write it in symbols first, but I want you to type in the chat window and tell me what that is. But this is what the product rule says. The first times the derivative of the second plus the second times the derivative of the first. And you don't have to write this middle step that I wrote in here, but I did that. So if you look back at it later and you can't remember what we did. Okay. So I need to know, what is the derivative of x minus 2? Yeah, good. The derivative of x is 1, and the derivative of minus 2 is 0, so that's just 1. And you could have just written e to the x. I just wrote the 1 there for emphasis so everyone can see where I got it. And then we have x minus 2 times the derivative of e to the x. What is the derivative of e to the x? E to the x. Yeah, the derivative of e to the x is itself. So that's it. I'm just going to combine like terms. So notice if I distribute here, I would have e to the x plus x e to the x minus 2 e to the x, or x e to the x minus 1 e to the x when I simplify. You could factor the e to the x out if you want. Okay. Again, my strategy is kind of to mess with it as little as possible until I need to. Later, we will need to factor that out. But for right now, we're just finding the derivative. And if you have a question about that, please let me know. Okay, though the second example, I see that radical in there. You see that cube root of x? Yeah, so the first thing I'm going to do is rewrite it as x to some power. So notice I didn't write y prime, I just wrote y equals, because this is the original function. The cube root of x is x to the 1/3. So I have two different functions multiplied together. That's how I know I need to use the product rule. So we're going to do the same thing we did up above. If you're comparing to the rule at first, just to point it out, if you're having to go back and look at it, which you may need to write it first, but practice enough that you just know it. But I'm going to take the first function, which is e to the x, times the derivative of the second one. So remember, this is what I'm doing. And the derivative of x to the 1/3. We drop the 1/3 down front, decrease the exponent by 1. And then I have the second function, which is x to the 1/3, times the derivative of the first, but the derivative of e to the x is just e to the x. I'm going to rewrite it without those parentheses at least to give you time to get it written down and let me know if you have a question about it. But then I wouldn't mess with it a whole lot for right now. Okay, but please don't be shy. So any questions about that one before we go on? Takes a little practice using the product rule, but it sure beats having to go back to that function and using the definition of the derivative every time. Okay. The 1/3 goes with the x to the minus 2/3. It does. Notice these are all just multiplied together. So it's like if you have 2 times 3 times 4, that's the same as 2 times 4 times 3. Multiplication is commutative, so it doesn't matter which order you write those down. Usually we would write the number part in front of that term. But yeah, just so we don't have to write so many parentheses. Yeah, great question though. Okay, so any other questions about those before we go on? The next thing we're going to say is just a caution, right? I'm trying to make this small so you can see this example we just did at the same time. The derivative of a product is not the product of the derivatives, which means that when you take the derivative of this function that we did up above, so I'm just going up here and circling so you can see it. When I take the derivative of this function, notice I can't just say it's the derivative of e to the x times the derivative of x to the 1/3. You see, that would not give me the correct answer. That works for limits, but it does not work for derivatives. When you're taking the derivative of a product, you have to use the product rule or go back and use the definition of the derivative, but you probably would rather not do that. At least if I were you, I'd rather not do that. So make sure that you actually use the product rule. We also have a quotient rule, and it also goes back to the definition of the derivative. That's how I would prove it. It looks very much like what I did for the product rule, so I'm not going to take time to do that so we can practice using it some more. You just add or subtract the same thing on top and regroup, and you would get the quotient rule. But the quotient rule says if you're taking the derivative of a quotient, so notice we have f of x over g of x. So you can call them numerator and denominator. I just said top and bottom, so I'm going to say it the same way. The quotient rule says that you take the bottom function, notice g of x is on the bottom. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Sometimes people learn it by saying low d high. I'm going to write this down in case it helps you. Low d high minus high d low over low or low squared. Sometimes people say low. Do you see what that means? That means the lower one, that's what I'm saying is the bottom, times the derivative of the high one, the derivative of the one on top, minus the high one times the derivative of the low one over the low one squared. Okay, but it's kind of fun to say, I guess. Low d high minus high d low over low. If that helps you to remember the quotient rule, then that's awesome. When I first learned the quotient rule, I didn't learn that little saying, so I always have to write it down first to make sure I say it in the right order. So usually in class, I will say the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, but if you have the quotient rule written down, now let's practice using it. So here's our first example. I have y equals t squared plus 1 over t minus 5. First of all, notice that my independent variable there is t. So we are going to find the derivative with respect to t. So this is the derivative with respect to t. So if you're comparing it to the quotient rule up above, notice that my f of t is t squared plus 1, g of t is t minus 5. So when I find the derivative, I'm going to use the quotient rule. So I know that it's all over the bottom squared. I usually write that down first so I don't get distracted and forget that I have a denominator. That happens to people on the test sometimes. So I just write it down so I don't forget it. Okay, but for the top, you are always going to say the bottom function, that's t minus 5, times the derivative of the top. So I need to find, and for this one, I'm going to put in this extra step here. So if you look at it later, you can remember what we did in class. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom. And if it helps you keep things straight, then put that extra step there in, but I won't require that you put that extra step there in, but be careful. Now I'm going to rewrite it. So I have t minus 5 times the derivative of t squared plus 1. So what is the derivative of t squared plus 1? Now, what about everyone else? Can everyone tell me what that derivative is? Yeah, you guys are exactly right. Yeah, that's 2t minus t squared plus 1 times the derivative of t minus 5. And we know the derivative of t is just 1. The derivative of 5 is 0. So that's it. I'll give you a hint about simplifying. Don't multiply the bottom out. When we use the quotient rule in the next chapter and we have to simplify, you will want the bottom factored. So leave it factored. But the top, notice we have two different terms because of this minus. So we need to simplify the top. We're going to combine like terms. So notice I have 2t squared minus 1t squared. And then minus 5 times 2t is minus 10t. And 1 times 1 is 1. So that's the derivative using the quotient rule. Notice that I cannot just take the derivative of the top over the derivative of the bottom. So that caution is on another slide. It says the derivative of a quotient is not the quotient of the derivatives. That means you can't just take the derivative of the top over the derivative of the bottom. If you have a quotient, you have to use the quotient rule to take the derivative if you're not going back to use the definition. But any questions about that first example before we go to the next one, because it looks a little bit harder than the first one? Okay, so the next example, notice I have a quotient. So I'm definitely going to be using the quotient rule again. So when we take this derivative, okay, using the quotient rule, I know that the bottom is squared. And notice I have the bottom times the derivative of the top. But notice in top, do you see we have a product? So I'm going to put this extra step in here because I want to make sure that you see what I do there. So this is the quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom. Okay, so that's what the quotient rule says. Sorry, I wrote that first one so big, so I'm having to squeeze that in there. And don't let me get ahead of you. So if you need a minute to catch up writing, please tell me that, because I want you to be able to work along with me. Okay, so I rewrote the bottom. Okay. On top, we have t squared plus 3. Okay. Now I have to take the derivative of t e to the t. So I want you to help me out here. If I take the derivative of t e to the t, what rule do I have to use there? What rule do we use when we take the derivative of t times e to the t? Do you see that's two different functions multiplied together? And anytime we have two functions multiplied together and we're going to take the derivative, we have to use the product rule. So in the middle of this quotient rule problem, we're going to have to use the product rule. but that's okay. We know how to do that. So now I'm using the product rule just on this little part. I have the first times the derivative of the second, but the derivative of e to the t is itself, plus the second times the derivative of the first, but the derivative of t is just 1. And then the derivative of t squared plus 3 is just 2t. So that's the derivative of that one. That's the derivative of that one. Any questions at all about how I got that? So let me hear from you. Okay. So let me know if that's okay or if you need a minute to ask a question. Thanks, Garrett. I appreciate that. So I know I haven't lost you. What about everyone else? Okay. You will start getting a feel for how much to simplify those. Okay, but again, you know, it kind of depends on what we're doing, how much we would simplify. Daniel, still confused on the part where I use the product rule. So let me go over to the side. Thank you for asking that, Daniel. So over to the side, I'm going to just do that part. So when I think your question was, what happened when I took the derivative of t e to the t? Okay, so for just that little piece, okay, when we find the derivative of that product, this is our first function, t to the first. Our second function is e to the t. So the product rule says we take the first one, which is t, times the derivative of the second one, plus the second one, times the derivative of the first. And the derivative of e to the t is itself. And the derivative of t to the first is just 1. That is how I got this part that's in the brackets there. You are very welcome. We could multiply all of that out if we wanted to. I'm not going to take time to do that on this one. Okay. We could also factor an e to the t out of the top. But again, but I am going to simplify this. This is all just one term. So just to make it look better, that should be a minus. That would be the same as 2t squared e to the t. And when we do these in chapter 4 and we're using that derivative to do something, we would need to factor that e to the t out of the top. But right now, let's just get used to using the derivative rules. Okay, but any other questions about that one? It was definitely harder than the other example. The quotient rule takes practice. Okay. Now, next problem, it doesn't look like we need to use the quotient rule, but, and in fact, just in case we don't have time to do both of these, they're very similar. Let's do example number 2 because we'll need to use the quotient rule on that one. It's just like example number 1. All right, but the question says, find the equation of the tangent line. So again, I'm going to do number 2. And we know, okay, to find the equation of the tangent line, we need to find the derivative because that's going to give us the slope of the tangent line at any particular point. So the first thing I'm going to do here is find the derivative. The directions do not say use the definition of the derivative. That means I can do it whichever way that I want as long as I work it correctly and show my work. So I'm going to use the quotient rule. I wouldn't use the definition of the derivative unless it told me to, right? Okay, so I have a quotient. So remember, okay, low d high, so I take the low one or the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And make sure you don't leave it like that. You have to actually evaluate those derivatives. Okay, but that means we have x times the derivative of e to the x, but the derivative of e to the x is itself, minus e to the x times the derivative of x, but the derivative of x is just 1. Okay. So if the problem just said find the derivative of that function, we would be finished. All right, so that's our derivative. All right, that's the new part. The rest of this problem you've done many, many times now. Right, we're going to write the equation of the tangent line at the point a equals 1. So remember, you need to find the slope at that point. So your slope is what you get when you evaluate your derivative at 1. So everywhere there's an x, I'm going to plug in 1. So notice here I would have 1 times e minus e to the first over 1. So this time our slope turns out to be 0. By the way, your slope won't always turn out to be an integer. If you ended up with a slope of e squared, then write e squared. Don't change it to a decimal. Whatever it is, it is. Okay, and maybe we'll even evaluate this one at another point just to make sure you catch what I'm saying there. But the slope is 0. The other thing I need is a point on my graph, and the x-coordinate is 1. So what's my y-coordinate? If the x-coordinate is 1, what's the y-coordinate? Yeah, e. And again, don't change that to a decimal. Leave an exact answer. Well, as soon as that slope is 0, you could probably just write the equation of that tangent line now, but I'm going to go ahead and write it in slope-intercept form. So I have y minus the y-coordinate is the slope times x minus the x-coordinate. But of course, 0 times anything is just 0, so we get y equals e. And that makes sense. It's a horizontal line because the slope is 0, so at least that matches. But any questions about that example? So I have that big red warning there, but I've already said it. The derivative of a quotient is not the quotient of the derivatives. When you find the derivative of this, you can't just say it's the derivative of the top over the derivative of the bottom. That does